Okay, this is section 4.8, complex numbers. And our objective with this section is to be able to divide and simplify complex numbers. Okay, just some kind of steps to go through as we're going to talk about a couple things here to begin with. Number one, you must multiply by the complex conjugate of the denominator in order to simplify the expression. And we're going to talk about what complex conjugates are and how you find them. Number two rule is that you cannot have I in the denominator. Okay, the reason you can't have I in the denominator is because you have a square root, and we cannot have any square roots in denominators. If it is still in your expression, then it's not simplified. Okay, and then number three, complex conjugates are always the opposite of the imaginary number, and the real number stays the same. And that's what we're going to talk about at first, is to figure out, okay, how do I find the conjugate? Okay, so let's take a look here at a couple of examples. Writing the conjugate of a complex number. Okay, first thing that you're going to do here on these, and I'm going to put this down here on the bottom. Okay, the first thing we're going to do is we're always going to take the opposite of the imaginary number. Okay, always take the opposite of the imaginary number, and part 2 says the real number stays the same. It doesn't change. So if it's positive, it stays positive. If it's negative, it stays negative. Okay, so let's take a look here at first example. As we look at this, it says write the conjugate of the complex number. Okay, so remember, to find the conjugate, we take the opposite of the imaginary number, and the real number stays the same. Now, if there isn't a real number there, then we just take the opposite of the imaginary number. So the opposite of 5i is negative 5i. That's the conjugate. Okay. Number 2, now I've added a real number in there, so now we have 3 minus 2i, and we have to find the conjugate of that number. Okay, again, the real number stays the same, so this is still 3. The imaginary number right here is going to change. It's going to become its opposite. The opposite of negative 2i is positive 2i. Okay, number 3, the real number stays the same, so the real number stays as negative 2. The opposite of negative 5i is positive 5i. Okay. Again, as you look at these examples, it's always going to be the opposite of the imaginary number. Real number stays the same. Now, number 4 is written a little bit differently. I put the imaginary number first, and we've always said you can't have the imaginary number first. We want the real number to be first. So as I go through this, I'm going to rewrite this as negative 2 plus I. Okay. So now, the real number is going to stay the same, negative 2, and the opposite of the imaginary number is negative I, and that's the conjugate. Okay. Now, why is it that we're finding the conjugate of these numbers? Because when you multiply by the conjugate, okay, when you multiply a number by its conjugate, what's going to happen is you're going to be able to eliminate your I value. For example, if I were to take these two up here on number 1, 5i and negative 5i, and multiply them together, okay, I'd end up with negative, okay, I would end up with negative 25i okay. As I look here, I'd end up with negative 25 I squared. And remember, I squared is negative 1. So now I've got, essentially, I'm going to change this negative 25 to positive 25. And you'll notice you eliminate your i's. Your i's are eliminated. So the complex conjugate is going to be able to eliminate our I value in the denominator, as you're going to see coming up. Okay, so now you know how to find the complex conjugate. Now, where are we going to use that? Okay, so let's take a look at the next page here, and let's take a look at some of these examples. And let's move this. I'm going to put this down on the bottom so you have some space to look at this. Okay, step number one as we look at this again, in order to, you cannot have I in the denominator. Okay? You can't have I in the denominator, so I cannot be in the bottom because it's a square root. Okay? So in order to do that, in order to get I out of the denominator, you multiply by the conjugate of the denominator. Okay? So in order to get rid of the I in the denominator, you're going to multiply by its conjugate on both top and bottom. Alright? So we look here at some examples. And let's take a look at number 5. Okay, we have 9 plus 12i divided by 3i. And as you look at this, the first thing you want to do is you want to identify is there an I in the denominator? And there is. Okay? This is your number that's in the denominator. And we can't have that I there. So I'm going to multiply here by the conjugate on both the top and the bottom. And the conjugate is negative 3i. And I multiply by the top and the bottom because as you multiply the same thing on top and bottom, that has a value of 1. So I'm not changing the value of my problem, I'm just changing what it looks like. Okay? It'd be the same thing as saying, okay, if I have $1, I have a dollar bill or I have 4 quarters. I can pick and choose. It's still the same amount, but I can pick and choose how I want it to look. Okay? So when I multiply this through, I end up having on the top, I've got negative 3i times the quantity 9 plus 12i, all divided by 3i times negative 3i is negative 9i squared. Okay? And now I've got to distribute on the top, which is essentially what we did yesterday. Okay? So now I got to distribute on the top. When I distribute on the top, I get negative 27i minus 36i squared, all divided by, I squared is negative 1, so that becomes positive 9. Okay? And again, as I look at this, we've got another I squared up top, so I can make this negative 27i and make this plus 36 and divide it by 9. Okay? Alright, now, can I have that I at first? No. So let's change the order of this guy. This is 36 minus 27i all divided by 9. Okay, and if you'll notice, all 3 of these numbers here are all divisible by 9. So and they all have to be divisible, because here's how you break this apart. This is the same thing as saying 36 over 9 minus 27i over 9, which 36 divided by 9 is 4, and 27 divided by 9 is 3, so I end up with 4 minus 3i. And that's my final answer. Now you'll notice you don't have an imaginary number in the denominator anymore. Okay? Alright. Now let's take a look at number 6. Okay, so as we're looking at number 6, now you'll notice in the denominator I don't have a monomial there anymore, I have a binomial. So I'm going to have to multiply by the conjugate because I have an I in there. So the conjugate of 1 minus 4i is 1 plus 4i. And I'm going to do it on top and on the bottom. Okay? And now I've got to FOIL the top and I got to FOIL the bottom. Because now I've got two binomials multiplied together. So this is where it builds on the multiplication piece. Okay, so FOIL, FOIL the top. 2 times 1 is 2. The outsides is 8i. The inside is 3i. And the last is 12i squared. Okay, and then in the denominator, if I go first times first, I get 1. Outsides, I get plus 4i. Insides, I get minus 4i. And last, I get negative 16i squared. Okay, now we just have to simplify the top and the bottom. And you'll notice, if you look at the bottom, on the bottom, these two middle terms, 4i and negative 4i, are going to cancel out for us. Okay, so as I look at this now, on the top, I'm going to have 2. I'm going to have 2 on the top. 8i and 3i is 11i. And the 12i squared now is going to become negative 12. On the bottom, I've got 1, and then this negative 16i squared here is going to become positive 16. So essentially, I have 1 plus 16. So 2 and negative 12 are like terms. That's negative 10 plus 11i. And then I'm going to divide that by 1 and 16 is 17. Now, as I look at this fraction, can I pick a number that will go into all 3 of these at the same time? No. So this is my final answer right here. Negative 10 plus 11i over 17. Okay. All right, let's move along and let's take a look now at 7 and 8. Again, on 7, we're going to multiply by the conjugate, which is negative 1 plus 4i. And on the top, we're going to multiply by negative 1 plus 4i. Run out of room a little bit there. So when I do it on the top, I got a FOIL, because again, I've got 2 binomials. So first times first is negative 4. Outsides is 16i. Inside is 3i. And last is negative 12i squared. And on the bottom, first times first is positive 1. Outside is negative 4i. Inside is positive 4i. And last is negative 16i squared. Okay? And now we've got to simplify it. Again, on the bottom, your middle terms, these guys are going to cancel and make 0. Positive and negative opposites of each other. Okay? So on the bottom, I end up, again, with 1 and then plus, this becomes positive 16. Okay? On the top, I've got negative 4. And I've got 19i. Because 16 and 13 is 19. And then I've got plus 12 because, again, I squared makes it the opposite sign. So then positive 12 minus 4 is 8. Plus 19i. All divided by 1 and 16 is 17. And again, is there a number that will go into all 3 of these guys? No, there's not. So that's your simplified answer. Okay. And let's take a look at this final problem here. You'll notice on the top we just have a number now, but on the bottom we've got imaginary numbers, so we've got to multiply by the conjugate again. So we've got real number stays the same, and the imaginary number is the opposite. Okay? So now on the top I've got 4 times the quantity 2 plus 3i. All divided by, and I'm going to FOIL the bottom here. So if I FOIL the bottom, I get 4. First times first is 4. Outside is positive 6i. inside is negative 6i, and last is negative 9i squared. On the top, if I distribute that, I get 8 plus 20 or plus 12i. On the bottom, again, my middle terms are going to cancel. And I've got 4 and then plus 9. And then to simplify it up, to finish it up, I've got 8 plus 12i, all divided by 13. Okay. All right, so now I've given you some examples of dividing complex numbers. So now we should be able to take any operation we want, add, subtract, multiply, and divide, and use all these complex numbers and be able to do these. This concludes section 4.8, dividing complex numbers.